So now that we've looked at the four primary components of an ignition system, the spark plug, the coil, the switching device, and the power source, let's talk about the system and put them together and how they work. And first of all, let's understand that there are some basic categories of systems, if you will. We can divide it up a couple different ways. First of all, we divide them up and split them by the power source. So engines that have a Magneto power system are going to have significantly different components and functionality than systems that have a battery and use the battery for the ignition. And so that's one way that we divide them up. So we'll look at examples of both of those. The other way that they're divided up is with their switching type. And so primarily older engines, it's not exclusive, but primarily in older engines, they're using that mechanical breaker point like we talked about, examples that we showed of that. Newer engines are going to use solid state type of switching devices. So rather than mechanical switch it open closes, it's going to be a solid state type of a switch. So transistors and thyristors and different things like that we use to open and close that circuit give us that inductive kick, that big voltage surge that creates a spark across the spark plug. So let's look at a system, and I think the easier one for me to get my head wrapped around is a battery type system. So if we've got the energy source from the battery. And so let's take a look at that system. So these are the components of that system, the basic components. Here's the battery over here that's creating the current. We have an ignition switch here, so that's your key switch when you turn the thing on or off. So that's what that ignition switch is there. You see we have a coil over here, so this is the coil, that transformer thing that gives us that step up in voltage. And then over here is our switching device. This is the breaker point, or that solid state device that's going to give me that switch. It's going to break that circuit and give me that inductive kick. And then over here in the purple line you see is the line going to our spark plug. So let's look at what happens when there's not a spark going on. So I've turned my ignition switch on so the current can flow from the battery through my coil. So it goes through my coil and then goes through my switch back to ground. So I've got current flowing through here. And this is probably a 12-volt battery. It might be a 6-volt. It might be 24-volt, depending on what kind of vehicle you have. We're actually seeing some now looking at 48 volts on some newer, larger equipment. But typically, that's your 12-volt automotive type battery, or maybe on your lawnmower, 12-volt battery there. So there's 12 volts of pressure making current flow through this coil, go down here. So I've got a little bit of current. I've got 12 volts of voltage drop across this coil. Now the coil in there, this is the primary coil, is the orange. The secondary coil is the purple, and typically we have a bunch more of them in there, so we have a whole lot of secondary coils, and so we get that big voltage step up. All right, so we've got 12 volts going through here, and we might have like a 50 or 100 to 1 or more, 150 to 1, something like that. So typically what we would have out of this coil is about 200 volts on here. So we got 12 volts going here. We have 200 volts of pressure, if you will, trying to make current flow through the spark plug. Well, how much does it take to make a spark? We talked about that. 200 volts isn't going to cut it. We need like 20,000 volts. So we need another 2 orders of magnitude more voltage to be able to make that spark jump. So that current just kind of sits there and can't go anywhere. So nothing's flowing through here. All right. So that's kind of at the non-spark state. Now what happens when we open this switching device? So let's look at that example. So same system here. We've opened this switch device. So now when I did have current flowing through this coil and going over to ground, it can't go. So all that current stopped. And we said, oh, what happens when I've got that inductor and I all of a sudden stop it? That's that speaker pop when you plug a microphone in and out or whatever. And we get that big high voltage. Ooh, so there's a big high voltage, that momentum, the inductive kick, get a big high voltage in here. Your book talks about the magnetic field collapsing. I've never been able to really get my head wrapped around that magnetic field collapsing, but the inductive kick I can kind of see where you get a big high voltage spike. So that's the same thing. That's what happened. That magnetic field is collapsing, big high voltage kick. Now instead of going from 12 volts to like 200 volts, I got a whole lot of voltage here on this primary coil because all of a sudden it stopped and I get that real short momentary spike of voltage. Boom, that throws a whole bunch of voltage up here, and this gets up above the 20,000 volts that I need to make that current jump across this gap and then go down to ground. So, hey, there we go. There's how I get my 20,000 volts. So it's when the switch opens. As soon as it opens like that, it triggers a chain of events in here. Big high voltage makes it jump across the magnetic fields that are collapsing and doing all that kind of stuff. Pow! We get the big voltage spike. We get the spark over here that makes the thing go. Then we close the switch and wait for the next time when it's the right time for it to happen. And boom, we hit it again. So that switch just opens and closes over and over again. Okay, so that's how that system is working. So kind of two states there. We saw it with the switching device closed. When it opens, that makes the thing happen. So that's a battery system. And like I say, I can kind of get my head wrapped around that a little easier sometimes than these Magneto systems. And again, the Magneto systems, the way they work is I've got a coil in here, and you can kind of see this coil is sitting next to my flywheel. Here's my flywheel, and we'll see these components when we tear them apart in the lab and look at them. And the flywheel has cooling fins. It spins. It's connected to the crankshaft. So the crankshaft of the engine is right here. This flywheel is typically connected directly to that. So it's spinning and coming around every time that crankshaft comes around. Well, then it's got magnets built into it, so very strong magnets. And as those magnets come flying by this Magneto, they induce that current flow, so they make the current go through there. So they're pushing current through a primary coil, which is jumping over to the secondary coil. And then I've got some points over here that are opening and closing at the right time, either mechanically or electronically. I can do it with solid state, so there's a couple different ways that we can make that happen. And your book goes through those and explains how all those things happen. But that switching will stop and give me the current, or give me the air gap, the enough current to jump across that air gap in the spark plug to give me my spark. So it's these magnets moving by that coil that triggers or makes that voltage happen. It puts the voltage in there, induces that current flow, and makes the thing go. Okay, so let's kind of look at a breakdown of that a little bit more. We'll kind of go through this. You'll see a lot of similarities between this and the battery system. The only real difference is instead of the current source, the original energy source coming from the battery, the original energy source is coming from the coils, and that current was induced, or we started it flowing in there because the magnets are moving around. So in this picture, the last picture we showed you, we had the magnets were sitting stationary on the outside of the flywheel, and the flywheel is coming around. This kind of depiction, these magnets would be inside, or the coils would be inside the flywheel, so the magnets would be going around the outside. So we can design them either way. They can work either way. But you can see we have south and north poles of those magnets as they come up around here. When those magnets go past these coils of wire and the associated armatures, so we call these big things the armatures here. They're usually layers, laminated metal that the coils are wrapped around. But when those magnets go by there, they start to make things happen. They make electrons move around, and I start to get current flow through it there. So everything is going to happen in a split second as those magnets come past. So as the magnets come past, the first thing that happens is that it creates some current flow in the primary side of that transformer, the primary side of that coil. So I get current flowing through there. The switch is closed down here, so that current can actually flow to ground. So I actually get the current flow. I establish some current flow through that primary coil, which now, because of the magnetic linkage between the primary and the secondary coils, it actually gets some energy or gets some current wanting to flow in that secondary coil. The secondary coil is connected to my spark plug, but it can't go anywhere because I don't have enough voltage yet to be able to make that thing jump across there. So that's what happens as it's charging up. So now, what happens when it's time for the spark? When it's time for the spark, you can see I've got this cam lobe that's coming around. The cam lobe comes around. It pushes on this. The pivot point is right here for the breaker. So it opens that breaker. Right in here is the break point. Oh, so now the current can no longer flow through that to ground. So the current can't go anywhere. So it actually current goes for a very split second, very short period of time, actually goes into this condenser. And I mentioned that the condenser is a capacitor. It's like a storage device. So it's like a balloon if you think about it. So we're actually going to shove some energy in that condenser. It's going to blow up. If you could, imagine that. It doesn't actually blow up physically, but it kind of, as we shove energy in there, it takes that energy and stores it in there for a little while. So I shove that in there. But what I've done then, when I've opened that switch up, that has stopped the current flow. So now I trigger that whole series of events up here with the inductive kick, with the collapsing magnetic fields. When I stop the one, the magnetic field collapses. That screws up the magnetic field on the secondary coil. We got big high voltage spikes, and they jump all over the place. Now, I will mention that the other thing that happens here, now if you think about this, this is a mechanical switch that's opening up. So if I open this switch up, and I've got enough current up here to create sparks, what's to keep a spark from jumping across that switch? And instead of making a spark in the spark plug out here where I want it, I'm going to make a spark across these points. Well, that's one of the things that the condenser does for us. The condenser will keep that voltage from getting too high right away to make sparks jump across that gap. And that's one of the things that when you're doing engine maintenance on an older engine, if you've got the points here that are starting to get burnt, so they'll get black. It'll almost like you're starting to weld. Remember we talked about that arc is kind of like a welding arc. So if I start to get little bumps or divots or something like that on those point contacts, that's a good indication that this condenser is going bad because it's not doing its job in protecting the points down here and keeping the spark from jumping across them. So I just want that to open up without a spark jumping. So there's a little maintenance thing for you. So if the points are going bad, that could be one of the problems, that you've got a condenser going bad. And typically you'd replace them both. If you replace the condenser, you got it apart, they're cheap, you replace the points as well. So they both go in brand new. That also could be an indication of the wrong gap in there and so forth, that these are open and closing too much or not closing completely or something like that. So, at any rate, going back to what's happening here, I opened this switch, some of that energy went into that condenser there, that stopped the current flow up here, I get the inductive kick, the magnetic fields are collapsing, boom, now I get a big voltage, and so if I come over here, I've got energy now coming out of that secondary coil, going down into my spark plug, but look, I'm actually also recovering some energy from the condenser, so the energy from that condenser can also, that was stored up in there, remember we said it's kind of like, almost think of it as like a balloon. So we blow up the balloon just for a real short period of time, and then it squeezes that energy back out of it. Again, it doesn't do that physically. It doesn't change size, but we can think about it like that. So we fill it up, and then it pushes it back out. And when it pushes it through that coil, there's enough energy, enough voltage, give us that 20,000 or 30,000 volts or whatever we need down here at the spark plug to be able to jump across. Okay, so again, same kind of thing, same idea, where we've got that inductive stuff, the collapsing field or inductive kick or whatever, going across from primary to secondary coils to step up that voltage and make the voltage even bigger, and that gives us 20,000 volts, gives us a spark, and then we do it again, and we do it again, and we do it again, and we do it real fast. So you can think about how fast this happens too, because again, this crankshaft is rotating. We got to have, for every 2 rotations of the crankshaft, we have to have a spark. Remember, we got 1 power stroke on a 4-cycle engine. So thinking about this as a 4-stroke engine, on every 4th stroke, we have to have a power stroke, so we have to have a spark. And that happens on every other crankshaft rotation. So if I've got an engine that's running at 3,000 revolutions per minute, that means half of that, or 1,500 sparks per second. That's how many sparks I got to have. So whatever my crankshaft rotation speed is, half of that is how fast that thing has to spark. So that's 1,500 times a second that all this happens. So it's happening really, really fast. So that gives you an idea to think about there. Now, I mentioned one more thing about the timing on this. So again, it's really critical, and we will come back and talk more about timing. We'll go into more detail on that and the whole engine cycle. But when this spark happens is very critical. So we talked about, hey, if that piston is coming up and I light that fuel, we're compressing that fuel in that piston, and I light that fuel before that piston gets clear to the top, that's going to start to burn. I'm going to build up pressure, and it's going to be pushing down on the piston while it still has not gotten to the top of its stroke yet to come back down. And so I don't want that spark to happen too late. Likewise, or too early. So likewise, I don't want it to happen too late. So if that piston comes up all the way, it goes through the top and it starts back down, and then I light the fuel, I've missed part of that stroke. So I really want that fuel to be burning when that piston's at the top, so I've got the pressure right away and start pushing that down. Now, because of delays in ignition and the fact that when we light it, it takes some nanoseconds, really small amount of time, but it takes a little time for that pressure to build up. We actually do light that fuel just a little bit before it gets to the top of the piston. So, and that timing is very critical. So just a couple degrees right before it gets to the top, we light the fuel so the pressure doesn't build up too much before it gets to the top and starts back down. And that's when I get the big pressure build up and pushes the thing down. So that timing is very critical. So, and actually that timing will change based on the speed of the engine. So when it's optimal. So the faster the engine's moving, I may want that timing to be a little bit in front. So if you're thinking about degrees of rotation, I want that spark to happen a little bit earlier because, again, it takes so much time for that stuff to start to burn. I want the pressure to be up and really pushing on that piston when it starts back down. And so I may actually change that timing a little bit depending on how fast the engine is running. So a lot of that can happen naturally in Magneto type engine just because of the magnets as they're rotating faster past the coils and stuff like that. That'll actually change the time at when those sparks, when I get those big voltage spikes and everything. So that'll actually change the timing of when that happens up there. So on the mechanical breaker point systems, we used to actually just rotate this whole thing. So you would have a spark advance. You talk about a spark advance system. So when the engine speed goes up, you would actually have a mechanical arm on this that would rotate this whole thing. Again, this center shaft with the lobes on it around here, it's connected directly to the crankshaft. So it's always going to be rotating exactly with the crankshaft. But if I rotate everything on the outside, then I'm moving the points relative to that center shaft, and so I can change when that spark happens. Now in modern engines we do that electronically, so we got computers in there and the computers are sensing engine speed and crankshaft position and all that kind of stuff. So they do that electronically with sensors, and there's an optimum time and it changes with speed. Now a little bit of a history lesson. If you go back to antique vehicles, you ever see an old Model T Ford, so something from the 20s, you had the steering wheel, and they didn't have a gas pedal on the floor. They would actually have a throttle behind the steering wheel, so you'd actually pull the throttle, and that's how you would change the speed. You actually had a lever behind the steering wheel that you would change the speed. But they had another lever on the other side, and that was a spark advance. So as you sped the engine up, then you would actually advance your spark as well. And so you actually had to know a little bit about engines and be able to hear and sense how the engine was working to be able to adjust that spark advance, to be able to adjust basically turning this whole distributor here, turning that so that you get that spark happening at the right time, get the most power out of that engine. So we used to actually make the operators do that. Now, of course, it's all automatic, either mechanically like this or with modern engines, just with electronics. So I hope that helps us get our heads wrapped around how this all works. So the four components again: the spark plug, the coil, the switching device, and the power source. Make sure you understand the different types of systems, battery versus magneto, and the mechanical versus the solid state or electronic type of switching devices. And be able to think through and understand how that's working and understand the inductive kick, understanding how I get that big voltage spike. It's made even bigger because of going from the primary to the secondary coils across that magnetic linkage there, give me that 20,000 volts that I need to make a spark.